Hi everyone, and thanks for tuning into our video titled Exponential Growth and Decay. You probably saw exponential growth and decay models back in either pre-calculus or algebra 2, but I'm here to show you the calculus part of the program, so we're just going to get right into it. I'm going to start by reading this short paragraph to you out loud. It says, suppose we want to find a quantity y that increases or decreases at a rate proportional to the amount present. So I want you to highlight or circle or underline this terminology right here, at a rate proportional to the amount present. And before we go any further, I want you to come down here and look at this differential equation. So the dy dt part is the rate. This is the rate of change of y, and it's changing at a rate proportional to the amount present. So this k right here is called the constant of proportionality. So we're increasing or decreasing at a rate proportional to y, the amount present. So what I want to do right now with just that piece of information is kind of come off to the side, and I want to give you a concrete example. So say your dy dt, your differential equation, was 2y. Like we actually pick a value right here for k. So we're changing at a rate equal to twice the amount present. This just means that y is changing at a rate of twice the present amount. So this is all this little formula, this little differential equation is saying. So what I need you to memorize is that when you see this phrasing, something's changing at a rate proportional to the amount present, this is the equation I want you to go to. This is your go-to. Okay, then it basically sets us up with a point. It says if we also know a point, like we know the amount present at time 0 is y sub 0, then we can find y as a function of t by solving the differential equation. So this part right here is just saying, hey, we have this differential equation. Here is the point. So I'm going to write this point right here. So when t is 0, y is y sub 0. And that just means it's your initial y value. Time 0, y sub 0. So we're going to go ahead and solve this differential equation. Well, we know how to do that. We've been working on that for quite some time. So first we'll start by separating the variables. So I'm going to multiply both sides by dt, which will swing the dt over to the right-hand side, which will give me dy equals ky dt. Then I will divide both sides by y to move it to the left, which will give me 1 over y dy equals k dt. I will then integrate both sides of my equation. We've done this many times. The antiderivative of 1 over y with respect to y is the natural log of the absolute value of y. That should look familiar. And the antiderivative of the constant k with respect to time is kt plus c. Now we will solve for y, starting by setting y equal to e to the kt plus c. I dropped the absolute value bars here because I know that e raised to any power will be positive. Now I'm going to separate the kt and the c as we have done in the past and make it y equals e to the kt times e to the c. And then I'm going to turn this constant, e to the c, to what we know to be capital C, constant e raised to the kt. Okay, now we will find our constant by using the point that we're given. So where the y is, I'm going to substitute y sub 0. And where the t is, I'm going to substitute 0. Solving this, e to the 0 power is 1, which just leaves me with c on the right, and y sub 0 on the left. So my final equation here in solving this differential equation for y will look like this. Y equals y sub 0, right? I'm plugging that for the c, e raised to the kt. Final answer. So basically, anytime you have the phrasing that we have y increasing or decreasing at a rate proportional to the amount present from up above, okay, you're going to start with this differential equation, and so long as you have 0 y sub 0 as your point, this will be the result. Okay, so this is called the law of, what we just did here, this is called the law of exponential change. So this is what the law of exponential change says. If y changes at a rate proportional to the amount present, that is, dy dt equals ky, and y of 0 equals y sub 0, then this is what y is equal to. And we just proved that right there. Now, there's one added thing here where if k is greater than 0, that represents growth. And if k is less than 0, that would represent decay. The number k is the rate constant. So, like my example above, if your k starts less than 0, say you had dy dt equals negative 2y, then y would be decreasing at a rate of twice the present amount. So negative represents decay or non-growth. Okay, so let's get into some examples. I've got example 1 right here on the back of the worksheet. It says, suppose $100 is invested in an account that pays 5.6% interest compounded continuously. Find a formula for the amount in the account at any time t. Okay, so I'm actually going to start with a differential equation. So it seems that because my rate of growth here, it's growing at 5.6% interest. So to me, it seems that the change in the amount in the account, which we'll call y, the change in y with respect to t, it's growing at a rate equal to 5.6%, which will be 0.056, times the amount present. If you want 5.6% of what you got, then you multiply 0.056 times what you got. So we're growing at this rate. So this becomes my differential equation, and the 0.056 becomes my k. Okay, so to solve this, I'm going to go through the same steps that I went through on the other side. So I'll multiply both sides by dt, which will give me dy equals 0.056y dt. I'll divide both sides by y, which will give me 1 over y dy equals 0.056 dt. Anti-differentiate, which will give me the natural log of the absolute value of y equals 0.056 t plus c. Solving now for y, and I'll drop the bars, y equals e raised to the 0.056 t plus c. Separating, I'll have e to the 0.056 t times e to the c. Of course, this becomes capital C, my constant, and the rest comes along. And now I need a point to plug in to find my c. So I'm going to look back here. It said suppose $100 is originally invested. So that means that at time 0, when the account was opened, we opened it with $100. So this becomes my t and my y. So y is 100 and time is 0. And so you can see e to the 0 is 1, so c ends up being 100. So my final equation for y, going back to this guy right here, is going to be y equals 100 e raised to the 0.056 t. Now if you look at this and you compare it to the law of exponential change, if you look back here at this guy, we could have avoided a lot of work by simply memorizing this, because let's look at it. If we had followed this, then we would have known that y was equal to initial y, that was $100, e raised to k, that was the rate of growth, right? That was the 0.056 t. This is exactly what we got, but we did all this work. And doing all the work is fine. I'm just saying that if you want to memorize your law of exponential change, just remember, had we been losing money, this k would have been negative. Okay, so let's look here at part B. It says, when will the amount in the account be double the initial value? Well, we have an equation. I'm going to bring this down. This represents the amount in the bank account. Right here, this is the amount in the bank at time t. Okay, and t is measured in years, by the way. T is measured in years. So we want to know when, so for what time, how many years is it going to take for the account to be double the initial value? Well, double the initial value would be $200. So we want to set the y equal to 200 and solve for time. So now we're solving an exponential equation. So to solve for time, I'm going to start by dividing both sides by 100. This is going to give me 2 equals e to the 0.056 t. Now we've been solving these kinds of equations lately in our free response problems. We're going to natural log both sides. So we have the ln of 2 equals the ln of e to the 0.056 t. And by our rules governing logs and natural logs, we know that we can bring this exponent now down to the front. So 0.056 t natural log e. And the natural log of e is just 1. So the natural log of 2 equals 0.056 t. And to solve for t, we'll divide both sides by 0.056. And so I'm going to write t as an approximation because I have a feeling I'm going to have to round. If I type this into my calculator and get time, I am going to type in the natural log of 2 divided by 0.056. So I'm going to round to 1,000. So we'll say 12.378 years. 12.378 years. Whoa. That's a lot of time. So if you don't add anything to this account, you just let $100 sit there and ride this out, it's going to take 12.378 years for you to be up to $200. So I don't suggest this as a strategy to save money by any means. Okay, now that's all there is for the note sheet, but I do want to show you that it's not always about money. I mean, bank accounts, because they grow with interest rates, these are a great example for exponential growth and decay, but it's not always about money. So when you are doing your mastery over the next 2 days, let's just do one together that isn't about money. Maybe number 5 would be a good one. So check out number 5 that you're going to be working on. It says the decay equation. So that's kind of cool because it's about decay. The decay equation for radon-222 gas is known to be, now let me get some paper here because clearly this assignment doesn't give you enough room to work. but here it is. So if I'm doing number 5 in my homework, y equals y sub 0 e raised to the negative 0.18t. This is really nice because they give it to me. They also say that t is measured in days. They're asking me about how long will it take, so again, we're looking for time, the amount of radon in a sealed sample of air to decay to 90% of its original value. Okay, so we want the amount y to equal 90% of its original value, which I call y sub 0. So really all you have to do here is where this y is, you just want to substitute. You want this to be 90% of the original value, and you just set that equal to the rest of the equation, which will allow you to solve for time. So in doing so, you'll start by dividing both sides by y sub 0, which nicely will cancel that out completely. So 0.90 equals e to the negative 0.18t. I'll take the natural log of both sides, followed by bringing down the exponent to the front. Since the natural log of e is 1, I need only divide both sides by negative 0.18 to solve for t. So t is going to be approximately, now remember this is days, put this in here. So it was the natural log of 0.90 divided by negative 0.18. So it looks like about 0.585 days, so not even a full day. So 0.585 days, final answer. So you just have to read. There's going to be different types of problems that you're going to be working through. Some of them have to do with money. This one, number 4, bacteria. We just did radon. Here we have radioactive atoms, a wolf population, and oil. So there's lots of different scenarios for this model, but just work your way through it and just keep your mind on the law of exponential change and, of course, this formula dy dt equals ky, and you should be good to go. All right, thanks for watching.